So today we have James Reed, and it's a real personal pleasure to introduce James. James has now, despite his young age, a long association with Oxford. He was an undergraduate at Oriel before going on to do part 3 in Cambridge, the BPhil and the DPhil in Oxford. So I was James's tutor when he was an undergraduate, and I had this surprising experience of this first year undergraduate rocking up to Leibniz-Clark tutorials and writing these essays, which were the kind of thing I was used to seeing from graduate students. James is a phenomenon, now philosophy fellow at Pembroke. I've just had a quick look on Google Scholar, and there are 45 things listed, and even when you remove his reading list, it's still in the high 30s. So it's a great pleasure to have you speaking to us, James. A particular pleasure for reasons I think you might mention in a second. So over to you.
Yeah, thank you so much, Oliver. That was very kind. It's an especial pleasure to give this talk because, in fact, it's the first time that I've given the Thursday seminar as well. So I'm really looking forward to talking about these things with you all today. So what am I going to be talking about? Well, you can see I'm going to be talking about curvature coupling, electromagnetic wave propagation, and the consistency of the geometrical optical theorem. Not necessarily tremendously illuminating. When Oliver asked me for a title, the one that I wanted to give was this one. Electromagnetic waves always propagate on null geodesics. I was hesitating at the time because this is the title of the article with which I'm going to be engaging a lot, an article by the two physicists, Asenjo and Hojman, and they've given talks with this title as well, so I thought maybe I shouldn't give this title. I ended up giving this not very illuminating technical one, but I guess the one I should have given is this: do electromagnetic waves propagate on null geodesics, and should philosophers care? So what is the philosophical or foundational significance, if any, of those results? So what's this talk going to look like? Well, I guess it's kind of a physics sandwich with as the bread. So the meat of the talk, if you will, is a discussion of Maxwellian electrodynamics in the curved spacetimes of Einstein's general relativity. But we're going to sandwich that between the things we know and love, the current geometrical significance of the metric field, whether one can construct clocks in general relativity, and so on and so forth. So I'll start off by talking about, in fact, some of the things that Sam was mentioning last time, clock constructions and general relativity. I'll then go on to think about how these physics results bear on that question, and I'll return to the philosophical questions at the end. So in a bit more detail, I'm first of all going to tell you about the theorem which Sam proves in his 2013 paper, Light Clocks and the Clock Hypothesis, and the reaction to it, which myself, Tushar, and Niels Linnemann, who's on the screen over there, gave in our 2020 BJPS paper. I think a lot of what we said is still right, but just almost without thinking about it, Niels and I started going back to the Asenjo and Hojman papers recently and realizing that there was more to be said about them. And we ended up writing a physics paper about what they say, in some respects developing on what they say, in other respects criticizing them. That's now been published in Classical and Quantum Gravity, and that's what I'm going to tell you about in the middle of the talk. Having presented all of that stuff, we're then going to come back to the philosophical issues at the end and see what our updated verdicts about things like Sam's result might be. So hopefully that sounds all right. So let's start off with Fletcher's theorem and our reaction. So I'm going to start off by just reading you the abstract of Sam's paper. I think this has the virtue of also reminding us of what the clock hypothesis is. So here is the abstract of Sam's paper. He says, the clock hypothesis of relativity theory equates the proper time experienced by a point particle along a time-like curve with the length of that curve as determined by the metric. Is it possible to prove that particular types of clocks satisfy the clock hypothesis, thus genuinely measure proper time, at least approximately? Because most real clocks would be enormously complicated to study in this connection, focusing attention on an idealized light clock is attractive. The present paper extends and generalizes partial results along these lines with a theorem showing that for any time-like curve in any space-time, there is a light clock that measures the curve's length as accurately and as regularly as one wishes. So Sam is idealizing in his constructions, but the central claim is this: for any time-like curve in any space-time, there's a light clock that measures the curve's length as accurately and regularly as one wishes. That's what Tushar, myself, and Niels picked up on. And our reaction initially was something like this. What Fletcher says might well be true. In fact, we hesitated about that a little bit for reasons I'll go on to explain. in an idealized sense, but when it comes to physical clocks built from material fields, can it be correct? So you might think, what about the constitution of the mirrors in this light clock construction? So the light clock has two mirrors, light bouncing between them, the clock ticks every time the light gets back to one of the mirrors. And the thing that we focused on is what about the physics of the oscillating material, light? And our goal in our paper was to explore how recent work in the physics literature interacts with particularly the concerns about the oscillating material. So the stuff in the physics literature that we were looking at was a series of articles by these two characters. So we have Felipe Asenjo here and Sergio Hojman here, both big figures in physics in their own right. So Sergio Hojman in particular, very famous from the HKT theorem in geometrodynamics. So these are, big figures making serious claims. And in a couple of papers, one in Physical Review D, one in Classical and Quantum Gravity, they argue that by solving Maxwell's equations in curved spacetimes, you can show that light doesn't invariably propagate along geodesics. Moreover, they argue that although light does propagate along geodesics in the geometrical optics limit, which is something which I'll go on to explain, you can't always take that limit, also they claim. So on the back of that, here's what we said in our paper. The Asenjo and Hojman result relies on light propagation might throw a spanner in the works of the claim that Fletcher's clocks can invariably be constructed. Insofar as one cannot always take the geometrical optics limit, it might throw a spanner in the works of the possibility of the idealization as well. Having now done this new work with Niels, I think our updated verdicts are something like this. We'd still maintain one, but we're a bit more hesitant about two, and I'll go on to explain that. Okay, so that's the kind of intro philosophical stuff. Now we're going to jump into the main section of the talk, which is mostly physics, albeit I hope physics of foundational interest. And then we'll come back to this stuff in maybe half an hour or so. Okay, so does light propagate in null geodesics? Are Asenjo and Hojman right? What are the senses in which they might be wrong? What are the senses in which we might be able to analyze them? So here's a bit of background. So there's a lot of ways that one can justify the conventional wisdom that light propagates on null geodesics. So here are three. So the first is that in the geometrical optics limit, in which the ratio, in which the wavelength of the light is very small relative to the characteristic scale of curvature variation, you can show that light propagates on null geodesics. There's a good demonstration of this in, for example, Misner, Thorne, and Wheeler's book. Here's much more recent work. So Gödel and Jim Weatherall have shown that small bodies constructed from Maxwell theories track null geodesics in a technical sense of tracking, which we can talk about if you want. And the third goes back to stuff from the 70s. So solutions of the Maxwellian wave equation in curved spacetime have, the claim goes, an idealized signal speed of exactly c. Friedlander has a whole book about this stuff. There's also reasons to doubt the conventional wisdom, call it into question. So one has to do with the work of DeWitt and Grimm in the 60s, and what they showed by using the bitensor formalism, which I think of independent mathematical interest, is that when you think about the propagation of electromagnetic waves in curved spacetimes, this can be associated with a tail, which moves behind the wavefront at a speed less than c. And insofar as this tail becomes more pronounced with an increase in the gravitational field strength, tail production can effectively retard the wavefront to a subluminal speed from an operational point of view, at least. So that's one reason to start maybe thinking that the conventional wisdom isn't always true. There are some other reasons. So first, various QED effects might lead one to question whether this is always true. So there are good reviews by Shaw and by Butterfield here. The relevant literature is things like the Drummond-Hatherell effect, the Scharnhorst effect, and things like this. Some of this is also discussed in the last chapter of Harvey's book. And Asenjo and Hojman are carrying on in this tradition of questioning the orthodoxy. And what they do, which I've already gestured at, is first of all show that before taking the geometrical optics limit, light rays in generic spacetimes don't propagate in null geodesics in the sense that this dispersion relation is not zero. And second, argue that at least in certain solutions like the Gödel solution, you can't consistently take the optical limit in which that null propagation would obtain. So that's what those guys say. That's where they're situated in terms of questioning the orthodoxy. So my goals and Niels' goals in this new paper were the following. So first of all, we wanted to numerically solve the equations describing the propagation of light in curved spacetimes to secure a better quantitative grasp of how the group velocity of such waves could differ with that associated with null propagation. So we'd be kind of exploring and up agreeing with them here. Second of all, generalize them in the sense that we might want to introduce extra curvature couplings into things like Maxwell's equations. Think about non-minimal coupling or the ambiguities that you get from minimal coupling. That's something that I'll explain in a second, and how that might lead to further distinct physics. And in a sense, we're agreeing with them here. If you include more terms in your equations, you get weirder propagation of light, which kind of makes sense. But we're also critical in these regards. So we want to clarify exactly when you can and can't take the geometrical optics limit and what that means. And in that regard, we're now slightly more critical of the Asenjo and Hojman claims than we were back in our other paper. And we also want to be clear about the different notions of wave velocities. So not only group velocity, phase velocity, but front velocity, signal velocity, and assess the implications of all of the Asenjo and Hojman work for those other notions of wave velocity. So let me start off with some background on curvature couplings. So here's the inhomogeneous Maxwell equation for the vector potential in Minkowski spacetime. If I want to change that into an equation for general relativistic spacetime, the standard thing to do is to follow the minimal coupling prescription, where you take the Minkowski metric, you replace it with a generic Lorentzian metric field, you replace the derivative operators compatible with the Minkowski metric with the derivative operators compatible with this new metric. That's the so-called comma to semicolon rule, and you'd end up with something like this. Just replace the commas with semicolons. But it's been known for a long time that this minimal coupling prescription is ambiguous. And again, this is very nicely discussed in Misner, Thorne, and Wheeler. It can lead, in their terminology, to factor ordering ambiguities. So if you wrote that previous flat space-time Maxwell equation with the partial derivatives exchanged, which you can do because you can swap them, then minimally coupled and then swapped back, you'd obtain another term here, which couples to the Ricci tensor. And you can ask, well, which of these equations is right from the minimal coupling prescription? Typically, people reject the second one, which features coupling to the Ricci tensor. So, for example, Misner, Thorne, and Wheeler, right? Coupling to curvature surely can't occur for without some physical reason. And they use this as a way of not thinking about the second one. There's another thing that you could do, which I think seems reasonable. Interestingly, they don't mention it themselves, which is if you look at this term, it doesn't look very gauge invariant from an electromagnetic point of view. So you might reject it on those grounds. But I guess what Niels and I say in our paper is there's nothing per se abhorrent with that equation. And other cases of this kind of curvature coupling will lead to gauge invariant terms. So you can't just always rule them out on these grounds. I think the right thing to say is that you have to make a methodological choice when it comes to deciding which of these equations to investigate first. But the world could, in principle, without further investigation, still be described by either of them. So it's important to remember there are two different possibilities here. We need distinct equations, and there's no reason to expect that the physics associated with those things will be the same. And ultimately, only experiment might be able to adjudicate between them. So partly, we now want to think about the different possibilities for those curvature couplings and see what different physical predictions they might entail. Okay, so now let's go to Maxwell's equations in curved spacetimes. So here's the source-free version of a minimally coupled Maxwell equation. This is not in terms of covariant derivatives. Instead, I've written a partial derivative, but then used the square root of the metric determinant. This is the kind of trick that Dirac likes to do, and it makes this thing easier to solve. So if I take this and I use a plane wave ansatz, so I take A mu to be Z mu E to the I S, where Z is the amplitude and S is the phase. I know that the wave vector, as usual, is just the derivative of the phase. In flat spacetime, what you'll find is that k dot k is equal to 0. So at least in the sense of group velocity, the waves are propagating at the speed of light. Even in curved spacetimes, in the geometrical optics limit, you're going to find that k.k is equal to 0. What Asenjo and Hojman, one of the things that they show near the start of their papers is if you don't take that limit, then in fact you'll get something more complicated. They use this particular gauge fixing of A, but they show then that k.k is equal to this thing chi, which takes this form. So in general, k.k is not equal to 0 before you take the optical limit. So in generic spacetimes, before taking the optical limit, light doesn't propagate on null geodesics. Now, if I wanted to include the kinds of extra curvature coupling terms which I was talking about before, then one straightforward way, at least, of investigating this kind of possibility is just to stick in another term here. This term looks like the one from before, where I've got the Ricci tensor coupled to A. I've introduced this number Z, which just lets me dial up or down how strong this curvature coupling is. Of course, that's just one possibility. You could have other kinds of curvature coupling terms, and that's something that I'll come back to later, but this is a very simple one. And then if I look at this kind of equation, so Asenjo and Hojman investigate this stuff, and then we just stick in this thing as well. We're going to now numerically solve this thing and figure out what the group velocity looks like, and figure out how that group velocity might change when I dial Z up and down as well. And here's the prescription. So you want to now choose a particular space-time. Asenjo and Hojman choose a bunch. In one of their papers, the physical review D1, they choose FLRW space-time. We'll follow suit. So plug in that metric, plug in a transverse plane wave ansatz. Now you've got a differential equation for K. You solve that differential equation. And you can then plug in a particular value of R and of little k, the parameter in the FLRW metric. And what you'll get eventually is KR, this component of the wave vector as a function of omega. So then you can start investigating the phase velocity, the group velocity, that kind of stuff. This is just kind of a slide of asides, but I think it's important revision. So I'll just remind you of some different notions of wave velocities. So the phase velocity, if I've got some wave, is the velocity at which the wave crests propagate in some medium. That's given by omega over k. The group velocity is the velocity at which the overall wave envelope propagates, and that's given by d omega by dk. So just skipping ahead, phase velocity is the velocity at which these blue guys move. The group velocity is the velocity of the whole envelope. When you do a first course, like your first year undergrad course in physics, you'll tend to hear that the group velocity really represents the velocity of the wave. But in the physics literature, there are a few more notions of wave velocity which are important. So one would be the front velocity, which is the velocity at which a sharp front in the wave propagates. And that's going to be associated with high frequency modes. Essentially, just Fourier transform the wave, the sharp front is going to correspond to high frequencies. Also signal velocity. So you might wonder, regardless of how the group velocity, what that's looking like, what the phase velocity is looking like, how fast can a signal in the wave propagate? People talk about that as well. And people have proved various theorems about these two as well. So these are equally important as these two, I'd say. That's just to remind you about the different notions of velocity, which I'm talking about. Okay. So going back to the FLRW, plugging into that Maxwell equation in space-time idea. So let's plug in the FLRW metric. Let's plug in our transverse plane wave ansatz. After mushing it around a bit, we'll get this equation. Not very nice looking. But what you can then do is plug in a particular value of k from your FLRW metric, choose a particular radius, so plug in a value of r, and then you'll be able to figure out kr as a function of omega. So that's what Niels and I do. Then once you've done that, solve this equation and see what the relationship between these things is. And you get a graph like this, they often look like this, where you can see in this case, in this particular picture, I've got basically k over omega is equal to 1 along the brown line where z is 0, where that extra term is turned off. But as I dial up or down the extra term, things get wigglier and wigglier and look less like null propagation because omega over k or d omega by dk is looking less like it's just 1. In general, you would not find that even for the z is equal to 0 part, you get a perfect line here. So you can have non-null propagation even in that case. Okay,
So
yeah.
do you mean non-null propagation in FLRW spacetimes?
Yes, okay. And in other spacetimes as well. So in fact, that's kind of a poor choice of diagram, but yeah, you'd expect the brown line to be slightly wiggly as well. Okay. So in that sense, we're agreeing with Asenjo and Hojman. Before taking the optical limit, if you solve these equations, you can see that the wave group velocity, say, is not giving you the speed of light because of the wiggly nature of that graph. And in a sense, we're also generalizing them because you can show that when you stick in extra terms, the line becomes more wiggly, which kind of corroborates, like in line with what you would expect, right? The more coupling you have to curvature, the less likely you would think that light is going to just go on onto your d6 before you've taken the optical limit. Okay, but now we turn to the kind of more critical part of our interaction with Asenjo and Hojman. So this is the discussion of what this limit is. So Asenjo and Hojman, in their CQG paper of these two papers from 2017 that I've mentioned, suggest that certain wave solutions in, for example, Gödel spacetimes don't have well-defined geometrical optics limits. So they claim that there's no sense in which the electromagnetic waves can be said to move on null geodesics at high frequencies. And here's the kind of reasoning. So we rehearse this reasoning in the BJPS paper with Tushar as well. So here's the dispersion relation in Gödel spacetime, so k dot k, just thinking about what that looks like in Gödel spacetime. Asenjo and Hojman identify the optical limit with the high frequency limit where little omega goes to infinity. And they claim that that limit is successfully taken only if k dot k is equal to 0. But then if you do that, the right-hand side is not going to be 0 because of the presence of this big omega term. The left-hand side is going to be 0. And so something looks like it's gone wrong by trying to take the limit in such spacetimes. So that's the kind of origin of the claim that the optical limit is inconsistent in such spacetimes. So circa 2020, we agreed with them. I'm actually slightly unclear. Tushar and I have had various correspondences. I'm not quite clear whether Tushar and I still agree about this stuff or not, but it would be good to talk about it. Yeah, I'm now more skeptical that you can't take the optical limit in such spacetimes. I think that you can, because I think that there are different notions of limits, and I'm not sure that Asenjo and Hojman have chosen the right one. So just recall that traditionally, as I said before, the geometrical optical limit is the one where you require that the wavelength be much smaller than the scale of curvature variations. It's not obvious that just taking little omega to infinity gives you that. So, for example, just to focus on Gödel spacetime, you know that that big omega is related to the Einstein tensor via this equation. This is from Hawking and Alice, but you could find it in a bunch of places, where u is some normalized for velocity vector. So pretty straightforwardly, big omega seems to be connected with things that you would associate with curvature. So you might argue that it's more sensible to take the geometrical optical limit to be the condition where omega over omega goes to 0, or alternatively, but as Sam pointed out to me and Niels in email, not equivalently, little omega goes to infinity and big omega goes to 0. If I choose that limit instead, and I go back to that dispersion relation on the previous slide, well, because that big omega, let's just focus on this one, for simplicity. That big omega is going to 0. Actually, the limit is consistent. And light does propagate on null geodesics in that limit. So this claim is really sensitive to what you take the right limit to be. You've got to be a bit careful here. It's not like the little omega to infinity limit, the high frequency limit, is somehow unphysical. The question is just whether it's the right limit to take when you're thinking about the geometrical optics limit. Again, I'm really grateful to Sam for some correspondence on this, because he kind of convinced us that it's not an issue of physicality. Every point in this limit in the space of models has a physical interpretation. So I think it's too strong to say this limit is unphysical. It's just, is it representing what you want it to represent? Okay, so there's another limit, and that limit is consistent. And if you take that limit to be the geometrical optics limit, you can take the limit even in these spacetimes which Asenjo and Hojman regard as being problematic. So that's one sense in which we're now a bit more hesitant. I'll come back to the philosophical significance of that for light clocks and so on later. There's another sense in which you've got to be, I think, more careful than they are about what notion of velocity is at play by thinking about things like signal velocity, front velocity, and so on. Asenjo and Hojman just focus really on the group velocity in their article. So the last part of my paper with Niels is expanding on how the Asenjo and Hojman stuff interacts with different notions of light velocity. Just before I get onto that, one slide on Hojman. So Hojman has a separate paper, which I think is of interest as well. So building upon those papers with Asenjo, if you accept that light doesn't propagate or need not propagate along null geodesics when properly modeled by solving Maxwell's equations in curved spacetimes, then it seems like you're decoupling light from the null cone structure. Hojman accordingly takes these results as a motivation for redefining proper time. The proper time interval is to reflect the actual interaction of light with the background metric instead of the idealized behavior of light in that optical limit. I think there are interesting philosophical things to say here, which I'll get onto in a bit. One reaction is maybe this is too fast. It's not clear that the null cone structure is most sensibly tied to light propagation. You might say the proper time interval is better understood through the conceptual roles of encoding causal structure, quantifying distance relations between path connectable points, and so on. So are these facts simply about the behavior of electromagnetic fields sufficient for you to motivate you to redefine proper time? I guess that's the question. Hojman thinks it is. I kind of want to remain agnostic at this point, but I'll come back to it. But also, relevantly, the causal significance of the proper time interval is not necessarily endangered by finding superluminal group velocities, since such velocities are not straightforwardly linked to superluminal signaling. So here we get onto the different notions of wave velocities. So signal speed, the propagation relevant for causal considerations, presumably, is bounded by the front velocity, which for a general set of PDEs, as shown by Shaw in this 2002 article, Butterfield also cites this article, by the way, is given by this formula. So it's given, the front velocity is given by the omega to infinity limit of the phase velocity. Friedlander showed that the front velocity is always c in curved spacetime. So putting these things together, it looks like this signal speed is still going to be bounded by c, even in spite of the Asenjo and Hojman results. That, of course, doesn't even mean that the bound is always saturated. In normal dispersive media, i.e. where the group velocity is less than c, whatever the appropriate invariant is, such as water, causal influences propagate at velocity less than the front velocity. It was shown in this paper by Stenner and collaborators in Nature that even in anomalous dispersive media, where you have faster than c group velocities, causal influences still propagate at less than c. So similarly, the instantaneous signal speed of an electromagnetic wave in curved spacetime, you might think, should also be seen to deviate downwards from unity, even when you have superluminal group velocities. And the precise amount of downward deviation is going to be a function of the curvature length scale relative to frequency. When you take the optical limit, you'll still get the velocity of the signal speed going to c. Things get somewhat dialectically complicated here, so I've got a few more slides, but if I were in this audience, I would probably struggle to keep track of what I'm going to say, but so be it. So now let's think about introducing extra terms in Maxwell's equations again, say. So there are different terms before. So for example, a partial A squared term or a partial A term. These lead to non-null dispersion relations even in the geometrical optics limit. Herzberg and Sandora, this is a paper in JHEP from a few years ago, really, really nice, argue that in this case, superluminal signaling can only occur at scales smaller than a photon's wavelength. And so they argue that even in these cases where I've introduced different curvature coupling terms which spoil null propagation in the optical limit, it's still not operationally significant. Given that superluminal signaling events for a photon only endure at length scales smaller than its own wavelength, such signaling might be regarded as operationally meaningless. So they claim. So yeah, like I said, there's a lot going on here now. So I'll summarize all of these points about wave velocities. So outside of the geometrical optics limit, light in curved spacetimes does not in general propagate at c. Pache, Asenjo, and Hojman, taking the optical limit is always possible, and light always propagates at c in that limit, at least on our revised understanding of what the optical limit is. Even outside of this limit in anomalous media, there are grounds to argue that the signal velocity deviates downwards from c. Including certain extra terms in Maxwell's equations modifies the propagation of light outside of the optical limit, but still yields null propagation in the limit. So those are the kind of terms that Niels and I were investigating when making the graph earlier. but including other terms, the ones that Herzberg and Sandora investigate, might yield non-null propagation even in the optical limit. But even then, there's a question about whether that non-null propagation in the geometric optics limit is operationally significant. I guess moral of the story here is that talking about what the velocity of the light is becomes a very complicated business. So I think Niels and I have three main points to make. The first is, outside of the optical limit, Asenjo and Hojman are right, and you can generalize what they say by considering certain curvature terms. The second is that their claims about the optical limit being inconsistent should be questioned. And the third is that you should be sensitive to different notions of wave velocity. Group velocity is not the be-all and end-all of light propagation. So now let's come back to Fletcher's stuff. So in light of our further study of Asenjo and Hojman's work, the stuff that I've just been talking about, I think Niels and I would now have the following take on its significance for Fletcher. So the Asenjo and Hojman result on light propagation might well still throw a spanner in the works of the claim that Fletcher's plot can invariably be constructed out of physical fields. But even that being said, you've got to be careful when it comes to the different possible notions of wave velocity. So our original concern was that if the velocity of the propagating signal is all over the place and there's not always null propagation, then that's going to be a problem for Sam's clock construction, which assumes that this velocity of the propagating signal is the speed of light. First of all, just focusing on the group velocity, seems like, yeah, there are still problems in terms of whether a physical clock built out of Maxwell fields could represent Sam's idealized clocks. But you still have to be careful about the notions of wave velocity, because the lessons for the group velocity that Asenjo and Hojman talk about don't necessarily carry over to the signal velocity and so on. But the second point is the geometrical optics limit isn't problematic in any space-time, as they originally claim. There's no strong reason to think that this idealization isn't always available to Fletcher. That's what I would now say. So here's how I would now understand Sam, and you can tell me if I'm right or wrong. I'm grateful for chatting to him yesterday about this stuff. So this is connecting up with this talk last week. You stipulate that the metric of general relativity indeed represents distances and times. Theorems like that of the 2013 paper afford defeasible evidence that that stipulation was reasonable. Those distances and times align with those of material rods and clocks isn't guaranteed from the outset. As Sam said last week, the metric might in fact represent more or less well. The examples presented that we discussed in the 2020 paper don't spell doom for Sam's space-time philosophy, but they're completely consistent with this. These are just cases where the metric doesn't do a good representational job. I'm not actually sure I disagree with any of this. But we can chat about it. I think there's maybe more to say here. Talking also with Oliver and Tushar about this earlier this week. So Sam's a big fan, as he said, of reflective equilibrium methodological iteration, and I am too. So this is something which has been discussed a lot by Hassel Chang. This is a completely gratuitous self-report also by myself. I even wrote a philosophy of biology paper last year. It's pretty exciting.
Unforgivable. You can't plug yourself like that.
But maybe there's room for iterative ideas in this context too, of the following form. So let's go back to Tevez, where you've got this primordial metric field and some other fields, and you can construct this new metric field G tilde from a combination of the primordial metric field and the other fields. Maybe Sam would say something like this. I know Oliver doesn't like this. Consider Tevez and stipulate at the outset that G represents distances and times. Realize that material rods and clocks are in fact reading off intervals of G tilde. Revise your initial stipulation. Actually, it would have been better if I said that G tilde represented distances and times, and maybe even repeat the process after that. What Oliver said to me is he doesn't think things should go like this because you have enough evidence at the outset with Tevez to stipulate from the outset that G tilde is the thing which represents distances and times. You know how that object is coupling, or that object which is itself a combination of various other fields, is coupling to the material fields. If you study the equations carefully enough, you just stipulate from the outset that it's G tilde that represents distance and times. Fair enough, but I don't think that these points are mutually inconsistent. I think that you could study what you know about a theory and make some initial stipulation about what represents distances and times, and still iterate if you study the theory more carefully later on. Coming back to that Hojman point, maybe this is a way of understanding what he's trying to do as well. So started off saying that it was the metric that represented or had something to do with intervals of proper time, but eventually he says actually some other objectives. So it seems like what he's saying there can fit it into this mold. Whether it's a good move to make or not is another question. I still think he's too fast. He's making too much of a deal about the propagation of light. But cool. Realize I've actually bashed through this. Anyway, there'll be more time for questions. So I'll summarize as succinctly as I can. So Asenjo and Hojman are correct that light doesn't always move on null geodesics, but you have to remember that there are different notions of velocity, and showing these things for group velocity doesn't carry across to other notions of wave velocity as well. The claim that you can't invariably take the optical limit is suspect. There are different kinds of limits, and it's not obvious that the one they chose is best associated with the geometric optics limit as traditionally understood. So some of the claims in the BGOPS paper with myself, Tushar, and Niels have to be tempered. In particular, the points we make about the unavailability of the geometric optics limit. But I think one of our morals that you have to be attentive to the construction of physical clocks still stands. Whether that's a particularly novel moral is, I think, another question, but I kind of still like our paper. That such physical clocks don't always exist, however, is perfectly consistent with Fletcher's spacetime philosophy, and I'm not sure I disagree with him about that stuff. So yeah, thanks for listening.